Alright, so today we're going to be talking about the notion of convergence for infinite series, and we're going to be mostly focusing on the power series. So the idea of convergence is, we kind of looked at it before, it's the fact that, for example, if we have a geometric sequence with a common ratio r, then we know that so common ratio r, first term 1, then we know that whatever the sequence or the series is will converge to this value. And so we can have that equality between this and what the geometric series has. So that's the whole idea of convergence, like us being able to show an equal representation of a infinite series because it converges to a specific value. So let's talk about convergence for power series. So this is called the convergence theorem for power series. Essentially, if we're given a power series in the form of n is equal the sum from n is equal to 0 to infinity of c of n, which is just some constant, times x minus a to the n, and this is just like the representation or the general form of a power series. Given that, there's three possible cases. So case 1 states that there is a positive number r such that the series diverges for the absolute value of x minus a is greater than r, and converges for this. So I'll explain what this means later. So diverges for x minus a greater than r, converges for x minus a less than r, and may or may not converge at the equality points. And these equality points are known as endpoints. So that's the first case, and I'll explain it in further detail. The second case is our power series converges for all x. And then our third one is converges for x equals a, and that just, when x is equal to a, that means all our terms just evaluate to 0 and no other value. So basically, when we're given a power series, we have three potential cases. Either we converge for a range around a, so since our center is a, we converge for values around a, and the range of values on either side of a is r, and this r is known as the radius of convergence. And when we have a finite radius of convergence, we converge for all the values inside of that radius, and at the endpoints, we have to test specifically and treat those endpoints separately, because the endpoints may or may not converge. So either we might get that both the endpoints converge, one of them converge, or neither of them converge. So that's one possible case. And then don't worry if it's abstract right now. Practice will make it much more simple. The second case is like a pretty simple case where for all values of x, our power series converges. And then the last case is we only converge for this one value at a, and that's a value you always have to converge at, because when you have x is equal to a, then all your terms in the power series are simply equal to 0 if we just look at the summation, and for no other value. So in case 3, our size of our radius is equal to 0. In this case, the radius size is infinity since we converge for all values. And then over here, our radius is equal to r, right? So those are the sizes of the radius. And so often a lot of problems related to series and sequence, or yeah, infinite series, is one, finding out if not the series converges, and second, finding out the actual values at which we converge, and finding out the radiuses. So today we're going to learn some tests that prove tests that help us prove whether or not a power series converges, and we're going to learn how to find out the radius, and then on the next part we're going to learn how to test if the endpoints converge. So the first sort of test for convergence is known as the nth term test, and basically this is kind of logical, but in order for a series, like notice that for a infinite series to converge, its values must tend towards 0, right? Otherwise, if the values don't tend towards 0, then the summation is just going to keep increasing, and then we get no convergence. But if we have our subsequent values of the series tending towards 0, then we have a potential to have some finite value to which the sum tends towards. And that's exactly what the nth term test sort of represents. So basically, the nth term test says that the limit as n, so the number, the sequence number tends towards infinity, and this is the nth term, that nth term should be tending towards 0, and that's exactly what we kind of said over here. And that's also the same thing as saying that the limit as n tends towards infinity, the sum of the first n terms minus the sum of n minus terms also has to tend towards 0. So these two are these two limits represent the same thing, but on the left side we're representing the fact that the terms, as we increase the number n, the terms has to head towards 0, and then over here we're representing that the sum consistently gets smaller, or the sum starts, not changing, or the difference between the sum once we add the nth term and without the nth term should become 0, and that's saying that the nth a of n is simply equal to 0. So these two are saying the same thing, and the nth term is a test for divergence. So it doesn't so the nth term test is a test for divergence. It doesn't tell you, if you pass this test, it doesn't tell you for sure that the sequences will converge, but it tells you that the summation from n is equal to 1 to infinity of a of n diverges if the limit as n tends to infinity of a of n fails to exist or is not 0. So either the limit can fail to exist if a of n just continues to increase as n tends to infinity, or if it kind of converges to a non-zero value, then you're gonna have increasing sums as you continue increasing n, and that means that our infinite series is not going to converge to a specific value, and hence in either of those two cases we'll have divergence. So this nth term test basically is a test that if you fail the test, so if either the limit fails to exist or if it's not 0, then you can conclude that the series diverges. But if it does pass the test, then we know, at least we know there's a possibility that the series converges. So this doesn't tell you for sure that the series will converge, and in order to do that you need to do more tests. But let's kind of use this nth term test as like a first example. And the idea is we want to find radius of convergence for this summation. So from n is equal to 0 to infinity of n factorial divided or times x to the power of n. So basically we need to consider all the values of x in this power series and kind of see what's going on. And so the only thing we have learned to deal with, or the only thing related to tests related to power series we've learned is the n term test. So let's kind of use the term test and see what's happening at different values of x. So limit as n tends towards infinity of n factorial times x to the power of n. So we can kind of break this up into multiple cases. Whenever we were dealing with a exponential function, the idea is the exponential function can have two behaviors depending on what x is, right? So if x is greater than 1, then we have exponential growth. Whereas if x is less than 1, we have decay. And then if x is equal to 1, we just have like a constant function. So let's kind of work out those cases. So, and then if x is equal to 0, well, so this is constant function with value 1. And then if x is equal to 0, we have value 0. So those are like the four cases of an exponential function. And so if x is greater than 1, then what we have is as n tends towards infinity, not only do we have this factorial growth, we also have growth on this side. And so we fail our n term test because the limit as n tends towards infinity of a of n, which is represented by this, is well, does not exist. It goes towards infinity. Now, if we have x less than 1, while our although we do have exponential decay, so the limit as x tends to, or n tends towards infinity of x of n goes towards 0 for x is less than 1. Before we proved, or we've showed that the factorial function grows faster than the exponential function. So that factorial function with that n factorial will still grow faster than the rate at which our exponential function decays, and therefore will still, like, our nth term will still tend towards infinity. Now when x is equal to 1, our function just becomes limit as n tends towards infinity of n to the power of n factorial, and we can clearly see that the factorial function grows unboundedly, and so that will also tend towards infinity. And finally, when x is equal to 0, our limit is just 0, and then we pass divergence, or pass the nth term test. And recall that we had the convergence theorem for the power series, which gave three possible cases. Either we converge at a finite radius, or second case was infinite radius, or the last case was we just converge at one value. And in this case, it seems like our nth term test for divergence only, or the only time that we cannot guarantee divergence is the case where x is equal to 0. But in all other x's, we kind of showed that our function diverges. And because combining that with the convergence theorem for power series, it means that because like the power series must at least converge at one spot, and we have found that only one value does not fail the divergence test, it means that x equals 0 is the only value for convergence. So notice how we used both the nth term test and the convergence theorem for power series to kind of come at a value, or come at a radius and a suitable range of values for which we converge to. And in this case, it's only x equals 0 because that's our only case left over for the convergence theorem of power series. So that was an example. Now let's derive, or let's come up with more tests. So this test is called the direct comparison test. And so this test states that let this infinite series be a series with no negative terms. So we're kind of constrained at which power series can be represented. But if we have an infinite power series with, or infinite series with no negative terms, then our series converges if there exists another convergent series represented by the sum of C of n with all values of A of n being less than or equal to C of n. So this is very similar to the integral direct comparison test we saw, where if we can upper bound our specific infinite series that we're worried about with another infinite series, and we know that other infinite series already converges, that must imply that the lower bound also, or like the lower infinite series also converges, which makes sense logically, because if we know another series that always has higher values than the original series converges, it must mean that like if another function kind of takes on lower and lower values, then obviously it should converge. And hopefully you guys can find the analogous like the part B, which is also analogous to the part B of the direct comparison test for integrals. And it says that if an infinite series represented by the sum of A of n diverges, if there is a divergent series represented by the sum of d of n of non-negative terms with A of n greater than or equal to d of n for all n greater than n for some n, and for some n. And also here, this should also include for all n greater than n for some n. So this just states that we don't always have to have a perfect upper bound, just the fact that the second series must start having higher values than the original series after some finite value. And then that should continue to infinity. And similarly, if we have this summation of this series represented by the sum of d of n, which always takes on lower values after some point, doesn't have to initially take on lower values than the series that we're concerned with, and we know that that series diverges, then obviously the series that takes on higher values as we tend towards, as n goes towards infinity, that should also diverge. And hopefully like the rationale for both of these cases is pretty intuitive. But that was the direct comparison test. And let's use the direct comparison test to prove that the sum from n is equal to 0 to infinity of x to the power of 2n divided by n factorial squared converges on all x. So we want to prove that this converges, and so we are just concerned with this part A. And if we want to prove that this converges, we must have a function or a series that takes on like larger values eventually, and that series should converge on all x. And so one series that you might think of is the sum from n is equal to 0 to infinity of x to the power of 2n divided by n factorial. So all I did was remove the n factorial, the squared term of the n factorial, and over here the denominator is not squared. And what that implies is the fact that since our n factorial term is not squared anymore, this denominator value will be smaller in this case. So n factorial is obviously smaller than n factorial squared. And because our denominator is smaller in this case, x and our numerator is the same, that must imply that x to the power of 2n divided by n factorial is always greater than or equal to x to the power of 2n divided by n factorial squared, right? This should be pretty obvious because this, like, when you simplify this, you get something like n factorial is greater than or equal to 1. And so this equality holds true for any n, because the smallest n value you can take on is 0, and 0 factorial is 1. So we have shown that this series upper bounds this other series that we're concerned with on all values of n from 0 to infinity. And now all we have to show is this new series that we have created as an upper bound converges on all x. And if you remember the Taylor series for the exponential function, you'll realize that this is just the same thing as e to the x squared. And we know that this equality holds true on all x. So holds true on all x. And because of this fact that this Taylor series equality holds true on all x, we can now use the direct comparison test to say that since this is an upper bound to the original series also converges on all x using the direct comparison test. So hopefully that application of direct comparison test made sense. So now we're gonna talk about another test, and this test is called the ratio test. And so the ratio test says let this summation represent a infinite series. If the limit as n tends to infinity of the absolute value of a of n plus 1 divided by the absolute value of a of n is equal to L, then we have three cases. We converge if L is less than 1. We diverge if L is greater than 1. And inconclusive if L equals 1. Or like if L is not defined, and you can kind of think about that as diverge. Well, this test, like if L goes towards infinity, for example, then you can't say it's divergent because there's a possibility that the series is conditionally convergent, and we'll get into that later. But for now, if like this series has only positive terms, then we don't have to worry about conditional convergence, and these are the only really 3 cases that you need to worry about. And so that's the ratio test. And essentially, that's another test to determine convergence or not. And so let's use the ratio test for an example. We want to find radius of convergence. And notice we want to find the radius, not the exact interval, because right now we don't possess the tools to find the exact interval. We can only calculate the radius, because to find out convergence at endpoints, we need to learn a bit more. So find the radius of convergence for this term. And let's use the ratio test. So in order for us to have convergence, we need the limit as n tends towards infinity of the absolute value of the n plus 1 term. So n plus 1 times x to the power of n plus 1 divided by 10 times n plus 1. And well, n's always positive, so the only thing I need to keep in the absolute value is this x, and then I'm going to divide by the nth term, so n times x to the power of n in absolute values times divided by 10 to the n, and I can rewrite this as limit as n tends to infinity of n plus 1 divided by n, and then this 10 to the n will go to the numerator and it will be divided by 10 to the n plus 1, so I'll have an extra 10 over here. And then the other terms that are left over is simply the absolute value of x to the n plus 1 divided by the absolute value of x to the n. Then I can rewrite that as limit as n tends towards infinity of n plus 1 divided by 10n times the absolute value of x, since this has a higher degree. And the limit or the ratio test tells me that I need this value to be less than 1 for convergence. So n plus 1 divided by, so as n tends towards infinity, this limit will go towards 1 over 10 times the absolute value of x, since this fraction over here tends towards 1 over 10, and then we have that absolute value of x left over, because that doesn't depend on n. So we need 1 over 10 times the absolute value of x to be less than 1 for convergence, and that tells us that absolute value of x is less than 10. And therefore we know that if x is over here, then we have some value at x minus 10 to x plus 10, where we will have convergence, and then at the endpoints we don't know for sure, but that doesn't affect our radius. So we found out that the radius is simply equal to 10. So using the ratio test, we were able to find out the radius of convergence. Finally, there's other methods to find out convergence, and one such way is this idea of a telescoping series. So let's say we're told to find the sum of n is equal to 1 to n of 1 over n times n plus 1. So this is clearly not a power series, but non-power series, infinite series can still converge or not, and you have to use other tricks to sort of find that out. And so one way we can kind of deal with this is we can use our knowledge of partial fraction decomposition, and we can write this as the sum of n is equal to 1 to infinity, and the partial fraction decomposition of this is simply 1 over n minus 1 over n plus 1. You guys can confirm that. And now it's just the idea of using like patterns. So let's find the sum of just the first term. That's just equal to 1 over 1 minus 1 half. If we find the sum of the first two terms, we get 1 over 1 minus 1 half plus 1 over 2 minus 1/3. We find the sum of the first three terms. We get 1 over 1 minus 1/2 plus 1 over 2 minus 1/3 plus 1 over 3 minus 1/4. And then you guys can maybe kind of see the pattern where all these like middle terms seem to cancel out, and all we're left with is the first term and then this term. So like the sum up to the nth term is simply 1 minus 1 over n. And as n tends towards infinity, it seems like we have a converging value to what the sum will be, right? And that's the whole part about finding, like, convergence just means this, right? What will the sum be as we have infinitely many terms as we go towards n to the infinity? And that's just the same thing as the limit as n tends towards infinity of 1 minus 1 over n. And so this term will just go to 0, and so our sum will converge to 1. So this was not a power series, but we can still use tricks such as partial fraction decomposition and like seeing these patterns emerge as techniques to find out what sum our infinite series converge to. But when we have power series, we can rely on a few tests like they were covered in this, that like were covered today, to find out whether or not our power series converges or not.